If we're gonna get
so good.
like, what's the time in India right now? Two Indians on YouTube ad-libbing about like physics. Like, we're just gonna get a huge Indian audience. Like, it's it's like early morning there, right? No, it's not. It's like middle of the night.
Do you think that there'll be like a moderator that immediately appears here?
That's funny.
Okay, got it. Let's see.
Like, what's the time in India right now? Two Indians on YouTube ad-libbing about like physics. Like, we're just gonna get a huge Indian audience. Like, it's like, is this just delayed? It's like early morning. It's delayed by a couple seconds. Oh God, everything I say is going to show up on YouTube now. What a revelation. I mean,
anyway, we're live.
We're live. It sounds like we sound decent, no?
We do sound decent. We don't look great.
Our audience of one, speak for yourself, Bus. well, our audience of one, which is us, can hear us correctly.
And as a matter of fact, I think that this will probably not be viewed by anyone.
Yeah, entirely possible, but it's good practice for us.
It is very good practice. So let us begin. I'm Vasu Sham, a postdoctoral researcher in theoretical physics at Stanford University. I'm joined by
Raiz Lorgat, a graduate research fellow at the Perimeter Institute for Theoretical Physics.
So we have a physicist and a mathematician that walked into an empty classroom.
At MIT, no less.
Neither of us are affiliated there. Anyway, we walked into this classroom and we decided that we would tell each other interesting things about—
spin a little tale, yeah?
Yeah, about what we think is basic in our respective disciplines.
Yeah. And what they might have to say to each other and about one another. And for us, that just happens to be one of the most basic elements of complex analysis, a statement about complex analytic functions, and also one of the most basic statements in conformal field theory about the conformal ward identities.
Exactly. So we'll start with Cauchy's integral formula.
Absolutely.
And then we'll see it applied to physics, see it applied to conformal field theory.
I mean, you were telling me earlier, Vasu, that Polyakov really thought of conformal field theory as animating holomorphic analysis, as giving it meaning. And this really, made me think of Feynman's quip that physics is like what sex to masturbation is with respect to math. So
that's kind of what we're going for here.
Let's get some action in.
Get some action in.
So I think since I'm the resident mathematician here, I should get us started and at least state Cauchy's integral formula. I mean, I'll give a hint for how it's proved, but much more important for us is the meaning of Cauchy's integral formula, which luckily, once you have the formula, which like Cauchy's genius, he was able to derive through geometric arguments. Once you have this formula, you can interpret it very easily with a simple arithmetic substitution. But let's state the formula first and see what it says. So in order to do this, well, we can actually refer to this beautiful diagram over here. Imagine we have a region in the complex plane, which we call D. It's some potentially unbounded region. It might be the whole complex plane, or it might just be some little blob like we see here. And within that region, we pick a point and we call it C. For simplicity, for those of you who are not too familiar, you can just say C is the origin. So C is 0. You can translate the origin to anywhere. What Cauchy really realized is that because holomorphic functions solve Laplace's equation, they essentially solve some differential equations, they are harmonic. And that means that they're entirely determined on any closed region by their values at the boundary.
Well, that is very interesting, Raiz. So just so we can acquaint our viewers with this fact that holomorphic functions do solve the Laplace equation, I will turn over momentarily to the blackboard, if I may.
Yeah.
Just since we've got one here.
You want to write it up for us?
Yeah.
Go for it. So what does that mean? What does it mean for a holomorphic function to solve Laplace's equation? And what is Laplace's equation?
Exactly. So symbolically, Laplace's equation always takes the following form. Oh, everything is backwards. What you gonna do? What are you gonna do? And by this triangle here, I really mean the Laplacian.
Yes, which we can think of as essentially as the differential avatar of the metric.
Yeah.
On flat space.
We're in agreement. Okay, and now let's go down to 2 dimensions.
Absolutely. We're studying the complex plane, and the complex plane is real 2-dimensional. Even though it's complex 1-dimensional, it's any point of the complex plane is spanned by 2 real variables.
Exactly, which I'm calling x1 and x2. Well, if we had any audience, they may have told us whether this is legible.
But let's assume that our audience is capable of reflecting their visual input.
That's true, yeah, we definitely assume that. So our starting point is a Laplace equation in 2 dimensions. And as you said, x1 and x2 parameterize R2, which is kinda, that's the technical symbol for kinda.
Which physicists make copious use of every day. Mathematicians sneer at them with envy.
The magic of kinda. That's another name for this podcast. So I have 1 complex variable's worth of information in these 2 real variables. And what I'm going to do is make a change of basis, right? And since this is all backwards, I'm just going to go straight to describing what the equation here in terms of z and z bar looks like.
Yeah.
And that will be
So what this tells us immediately is that if a function f is annihilated by the differential operator del bar, which is the second differential operator in that quadratic expression in differential operators at the top, then it solves Laplace's equation. Because if it's annihilated by the first application of the differential operator, the second application applied to 0 is 0. And by definition, one can take a holomorphic function is annihilated by del bar. Of course, it might be a little bit of work to show that every such solution of del bar as a differential operator applied on, say, some function is actually holomorphic in a different definition of holomorphic, say, complex and analytic, in the sense that all derivatives to all orders always exist. But we'll leave that as an exercise for now.
Mm-hmm. So for the benefit of the physics-minded in the audience, largely imaginary at this point in time, but for their benefit, the intuition behind saying that the Laplace equation is solved purely in terms of boundary values comes from thinking about, say, electrostatics, where we have the inhomogeneous version of Laplace's equation, the Poisson equation, describing the relationship between, you see, the charge density, right, and the electric field.
Right.
So we basically have the potential determined through Poisson's equation. Right? And what we discover is that the profile of the charge density on the boundary of some region really determines the electric field within it. And so that's kind of what's going on here.
Absolutely. And in fact, what we will see in the statement of Cauchy's integral formula, which we'll return to in a moment after we clarify the geometry underlying it, which will make the statement accessible to our audience, what we find is that the structure of these complex analytic poles plays a central role in even understanding the meaning of Cauchy's integral formula. So let's first revisit this geometry. So we're inside the complex plane, and inside the complex plane, we have some open region, like which we're calling D here, which might be all of the complex plane, some open set, some blobby region. And we're interested in analyzing a holomorphic function defined on that region D. So holomorphic here means, as we just described, it's annihilated by the del bar differential operator, or equivalently, every derivative to every order exists and is continuous. Now, for such a function, we can pick some arbitrary point, say C, and we can ask, how do you characterize the value of the function at C? And Cauchy's insight stemming from this harmonicity observation is that one can draw a disk centered at C, and one can analyze the function's boundary values on the boundary of that disk, here denoted by gamma. And he found a relationship between the values of the function evaluated along gamma and the values of the function at C. And moreover, he found, in fact, that there's a relationship between the value of the function defined anywhere inside the disk and the values of the function at the boundary. So the precise statement, intuitively, if you've seen any mathematics in functional analytic terms, is that Cauchy's integral formula gives you an integral pairing. It says that one can take a simple pole defined at the location W within the disk and pair it, that is to say, just multiply it by the function f, and then take an integral of the resulting product around the boundary. And taking the average of this integral, that is to say, dividing by 2 pi I, one actually finds an expression for the value of the function f at W. So
reveal.
Let's look at that in terms of equations. We're looking at it over here. So that says that the function f evaluated at W is given by an integral pairing. Again, we take two functions, f, the function we're interested in, as an abstract function of a complex variable z defined on the disk. And we take another function, which is the simple pole, 1 over z minus w, and we take their product and we integrate the result along the boundary, which for us here is a circle. And we're interested in the average of that value integrated along the boundary. And Cauchy realized that this gives you a precise expression for the value. So that is to say, one can expressly describe a holomorphic function either in terms of its evaluations on the interior of the disk or in terms of its average on the boundary of the disk, which is quite a profound statement. It is, in essence, a restatement or a complex analytic version of harmonicity, an analog of harmonicity. So we won't give a proof of this statement today, though if there's interest, we can certainly do that. There's a really gorgeous geometric proof we have prepared. But what we
Please comment interest if there is interest.
But what we will do is we will derive harmonicity from this statement and then claim that actually this is equivalent. So starting from what is known as the complex version of the mean value theorem, which will arrive from Cauchy's integral formula, and a little bit of legwork, you can actually recover Cauchy's integral formula. And so you can consider this as a equivalent characterization of what a holomorphic function is altogether. And it is an essential characterization because, as we will see, it essentially leads to the conformal ward identities almost immediately. So before we do that, let's examine a consequence of this Cauchy's integral formula, which really just arises from an evaluation of this formula. And so to do that, specialize our point W, which we were previously allowing to roam inside the disk, specialize it to the center of the disk. So we force W to BC. And we also now give an explicit parameterization of the boundary circle of the disk by an angle theta. So you can pick an arbitrary point to be the 0 angle. And then as we move around 0 to 2 pi, we sweep out this closed contour. And in a formal arithmetic expression, all we're really saying is that we can translate the circle of radius r by the complex value c to get a path described by the phase angle. So for every phase angle, we get a point of the complex plane, actually a point of D, which lies on this boundary, gamma. And now it is really just a straightforward computation, which is, by which I mean just a substitution, to show that F applied to W, which is now C, is given by this integral pairing. And now, since we have an explicit evaluation of the contour along which we're taking the integral, we get an explicit evaluation of the integral itself, which leads to the exact statement of harmonicity. And so what used to look like an integral pairing of a function with a simple pole against our holomorphic function is now literally an average over the boundary circle, or over all phases. And so here we see directly, if you want, a derivation of the fact that holomorphic functions are determined by their boundary values on any closed connected domain.
But you see that we should also appreciate the fact that the expression over here completely hides the fact that the integrand has a pole.
Absolutely.
Z equals C, which again tells us something about the nature of the angle as a coordinate.
Absolutely, absolutely. Like what is being reflected here, maybe getting a little bit too ahead of ourselves, is the topology of a circle.
Right.
I mean, the circle, in essence, appears as soon as one punctures the complex plane. As soon as you throw a single point away, then the circle retracts onto any circle of radius r bounded around that puncture. And that statement, a statement of topology or homotopy theory, is being reflected here in an extremely elementary fashion, which is to say, when we pair a holomorphic function against a pole, what we're really doing is transforming the problem into a real problem involving a phase angle variable. And we notice also that the 2 pi I in Cauchy's integral pairing disappears. And this is something I always found quite magical, is like, what is the nature of these divisions by 2 pi I? And they're intimately tied to these phase angle coordinate systems that naturally arise around any pole in the complex domain. And I should note, we're missing a 2 pi I over here, but we can fix that later.
We'll fix that.
Yeah. So now that we have this, we should probably turn to some physics, don't you think?
Yes, let's turn to some physics. But don't we want to first mention what residues are?
Yeah, we probably do. No, that's a fantastic point. So what you see over here is really just the first in a discrete family of Cauchy's integral theorems. What we're finding is the base case of a very generic structure, which is saying that in order to evaluate a function at a certain point, we can pair it with a function that has a simple pole. Now, you can ask, as Cauchy did, in fact, what happens if you pair it against a function with a higher order pole? And this leads to Cauchy's higher residue theorems, which is to say one can formulate an analogous statement which allows one, instead of evaluating the value of a function, so like the value can be thought of in the Taylor expansion, let's say f of w equals sum I equals negative. So I'm picking a Laurent expansion, in fact, here, not a Taylor expansion, because we are admitting arbitrary coefficients in, let's write them like this.
Probably want to brace that.
Yes, I do. This is what I get for typing in an alternative keyboard most of the time. So let's just consider
and we probably want to divide these out by.
Yeah. Do you want to do it? Because I can't talk and type at the same time.
Yes, tell me what you need.
Yeah. So divide by factorials.
Let's divide by factorials, but also by the powers.
Yes, and by the power z minus W.
Well, then we probably want to do this.
Yeah, we want to do that. Yeah.
So we have the derivatives, and then we have
Yeah.
the z minus w's to
Yes.
the power I minus 1, or is it just I?
Just I is fine because, I mean, it depends how we parameterize it. It's fine.
That's true.
Yeah.
And
then you can throw away the coefficient ci.
I guess we don't really need the coefficient ci here.
Right. So these kinds of Laurent expansions are entirely natural because from a purely mathematical point of view, you could consider that the space of all functions is really spanned as an infinite dimensional space by, in a linear sense, by functions with an arbitrary order pole at a given point.
So just to translate what that means, basically think about this as a sort of series expansion, right?
Right.
So this is what you were trying to go for before.
Yeah,
right?
I mixed two ideas in the middle of typing that up.
So what Rais is saying is that I have these W-dependent coefficients.
Right.
And then I have my poles, right? Which I have. So this is a simple pole. This is a pole of order I.
Yes.
Right. And this sum runs from minus infinity all the way up to plus infinity. Well, I guess it's really, since it's in the denominator, we probably don't want the minus here, huh?
Yeah, it doesn't matter that much.
It doesn't really matter.
Doesn't matter at all.
So let's just keep that aside.
Yeah. So really, again, what we're saying here is that there's some very strong local nature of holomorphic, or more generally meromorphic functions, where meromorphic means we allow poles. Right. So holomorphic means that the function is regular and has no singular behavior. Meromorphic means that the function may blow up at a single point. And that's what expanding into the negative index I, or in the sense the positive index I in our notation here is really doing, is it's allowing singular behavior because those terms will blow up. As we let Z approach W along any phase angle, those terms will blow up faster and faster as the depth of the pole increases. So what one can observe, starting from, in fact, Taylor's formula, and later on by the work of Laurent, that one can, in fact, express any meromorphic function in a small disk around any point, no matter the singular behavior, no matter whether it's regular or not, in terms of this infinite dimensional basis given by these poles of arbitrary order or no order. So, you could have a zero of order when I is negative here. And Cauchy's residue theorems is an acknowledgement of the fact that the very same idea as Cauchy's integral formula can be applied to not only evaluate the zeroth order Taylor coefficient, but in fact, any order Taylor coefficient. And the way one does that is to consider an integral pairing not against a function of an simple pole, but a function of pole to the order, say, k minus 1.
Let's do that. Let's just write it out.
Yeah, let's write it out.
So what Rais meant was that we have k, the kth derivative. So just to lay out our notation.
Yeah.
Right. What this means is that I'm taking the derivative with respect to z, k times of the function evaluated at z equals w.
Yeah. And quite important here, I do want to add, is that Cauchy's integral formula is the case in this notation k equals 0, which is the constant term, so to speak, when we consider an expansion of this function in a small neighborhood, in a tiny little complex analytic disk around the point W. Because one can see immediately that when z equals W, all the terms vanish, except for the 0th order terms, in the event that the function is regular. And when the function is singular, then the function actually blows up at that point. And so it is not well defined at that point. And so Cauchy's original integral formula simply evaluates to the observation that in order to pick out the kth derivative, or if you want in the negative direction, then one simply has to pair against a function of a higher order pole shifted by one. And the proof is extremely elementary. We won't go into the details here, but it simply involves applying the differential calculus.
It's an exercise for the reader.
Yeah, in fact.
Well, in fact, it's evident from what we're doing here. So all you really need to do is plug in the Laurent expansion.
Be clear to yourself about what these various formulas are actually saying. It's all expressed for us.
There's presumably some -1 to the k, something like that, but
yeah, I mean, it's not essential. It's really, really not essential.
Right.
I mean, the key idea, we're proceeding at a physical level of rigor here. The key idea is really that one can shift the evaluation procedure by pairing against higher or lower order poles, higher or lower order zeros, depending on which direction in the index you're looking at.
Right. And any output of this sort of procedure is something we call a residue.
Yes, that's correct. So
that's our
classically, the residues were known as the minus, I guess in our notation, the +1 index, I equals 1. And it was considered like the first polar part, namely that part of the function that determined the polar behavior for a simple pole. And then as the depth of the pole increased, those were considered higher residues.
Right.
But as we've really given a kind of like symmetric treatment to zeros and poles, which absolutely is the correct point of view in complex analysis, it really becomes clear that whether one considers zeros or poles is simply a matter of perspective.
No, for sure. So,
we have Josh.
That's pretty cool. Welcome, Josh.
So
hello.
Now I think we might be ready to derive the conformal ward identities from Cauchy's integral formula.
Yes. So let us begin. Let's share another screen now. Actually, I need a second. So the point was mainly to find a simple application or an application of the integral formula that took us directly to a result. Integral formula plays a key role in the middle in various physics-related stories, but what we wanted to see was a case where it was the silver bullet. And no place is better for that than the two-dimensional conformal word identities. So let's get to them. Oh yeah, Josh, we're streaming live on YouTube. I hope you know.
Cool. Yeah. I saw the warning sign before I came in, so
that's
why I
good.
turned off my camera.
Yeah, we're just having fun. We're improving our exposition skills, basically.
Yeah, you may anticipate correctly that no one's seeing this. And that's okay.
What? Nobody wants to learn about Cauchy's integral formulation on a Monday night?
No.
What a novel premise.
Yeah. Who knew that humanity was so lame?
Well, we're off. So to go a little slower with what I was doing on the blackboard, which was backwards to all our viewers, the basic idea to translate from real to complex coordinates is to make these linear combinations of the two real coordinates. And the object of interest to us is the energy momentum tensor, or the stress tensor, as I call it in these notes. So I have three components. It's a symmetric 2x2 matrix in the end of the day.
Yeah.
And so I have three independent components.
Spanned by a three-dimensional space.
Exactly. And what I have is a condition that comes from the scale invariance of the theory that the trace of the energy momentum tensor has to vanish. So I'll jump back and forth a little bit.
I mean, we can even say something about the origin of that condition,
Absolutely.
which is that the conformal symmetry extends a natural SL2C action. And
That's
so for
one
those
way to
of us
go.
who are familiar with some Lie theory, what you find is that conformal symmetry can be considered as an infinite dimensional extension of the Lie, at least at the infinitesimal level, of the Lie algebra of the complex matrix group SL2C. And so in degrees -1, 0, and 1, you actually find the Lie algebra of SL2C. And this is extended by infinitely many operators in the positive direction and infinitely many operators in the negative direction. And so the fact that the stress energy tensor is traceless is a manifestation that the core of the symmetry algebra for conformal invariance in 2 dimensions is generated in degrees -1, 0, and 1 by traceless 2x2 matrices.
That is a deep and profound point.
It really
except there's something that physicists like to do, which is write symbols like this.
Yeah, it makes them feel good.
Exactly. So what we're doing here is varying the metric within the action. The response of the action to varying the metric is the energy momentum tensor. Some people put a half. I don't really care. Now let's restrict to variations.
To 1.
Exactly. So let's restrict variations to those that just rescale the metric, right? So let's take x, g, alpha, beta. So this is an infinitesimal Weil transformation. And if, in fact, my action is invariant under these Weil transformations, then what that tells me...
Infinitesimal invariance really means that the exponential of the variation should be the identity, because we're dealing with Lie algebras or infinitesimal symmetries. That means to say when we flow by time evolution, we pass to an exponential by the Baker-Campbell-Hausdorff formula. And so 0 will exponentiate to 1, which acts as the identity. So the condition for invariance at the infinitesimal level should be that the variation is 0.
Exactly. Thank you for that, Raise.
The things they don't tell you in grad school.
For sure. I mean, we do have Josh here, who we will quiz later on to see if he's following what we're talking
give him an
about.
exam.
So just to see the set of manipulations that went on here, the stress tensor is defined as the response under the variations of arbitrary infinitesimal variations of the metric of the action.
Right.
I restrict to a specific variation of the metric, which is one under infinitesimal rescaling. In so doing, and in demanding the invariance of the action under such a rescaling, I immediately see that the trace of the energy momentum tensor has to be 0. Now, the exercise for our viewers is to translate the condition that the trace of the energy momentum tensor, it being 0, to the statement that the off-diagonal component of the stress tensor in complex coordinates is 0. Basically, you see that TZZ bar, because of the nature of the coordinate transformation, is equal or is proportional to T11 plus T22.
Yeah.
Right? And then we know that the stress tensor is also conserved. This is a statement of energy momentum conservation, essentially. Going back to this exercise, what we would look at is another variation, which is going to be reiterated in what follows. But it's basically the one where you take and then you symmetrize here.
So remember, restricted variation here just means we don't consider all possible variations, but we're trying to understand the symmetries of the system by restricting to a subclass of variations and trying to understand the infinitesimal response to the action.
So the response to this infinitesimal variation is the divergence of the stress tensor. That's another exercise for our viewers. What's nice is that having set t zz bar to 0, we discovered that d bar, I've written this as partial of bar z, but let's just bar it.
Bar the whole thing.
Just so that we know that it's the bar.
The del bar operator that we
Exactly.
were thinking about earlier.
So del bar of tzz that I'll call t vanishes.
It's also 0, which implies holomorphicity.
Exactly. And then the same is true of del of t bar. So the stress tensor has split into a holomorphic and anti-holomorphic.
Also known as the two chiral halves of the underlying conformal field theory.
Exactly. We'll be slow to take this statement of holomorphy seriously to mean that this is an innocuous holomorphic tensor because the stress tensor has an anomalous transformation property, but we'll set that aside for now. Classically, it is what it is.
It's perhaps maybe worth remarking on the nature of that word chiral. So chiral means handedness in regular parlance, not that people use the word chiral in everyday speech, unless you're a biologist.
Yeah, that's true.
But what it really manifests is that in holomorphic or anti-holomorphic coordinates, what one is really doing is one is applying what is known as a Galois transformation on the complex plane, which actually reverses the orientation of the complex plane. And so a circle that might be going about clockwise in a holomorphic coordinate, once you apply this Galois symmetry, is now reversed in orientation and is now going anti-clockwise. And this is the nature of chirality, which is to say what conformal field theorists call left movers or right movers in generic computations. So whenever one is dealing with this handedness, with this orientation around the fundamental phase circle.
For sure. You know, it would be nice if we could cut in like these wonderful animations of the effect of these Galois transformations on the complex plane, but that's
maybe for a future ambitious session.
Exactly, when we have an audience.
I love this notherology of the stress.
Yeah, let's do some notherology. So I'm just reiterating a calculation that I did before, just in a little bit more detail, with particular transformations in mind.
So now we're modifying the coordinates by some small quantity.
But notice that they're purely holomorphic
or anti-holomorphic, which only makes sense by the symmetry constraints that we just derived.
Exactly. And the t and t bar that we were talking about are basically the the holomorphy or anti-holomorphy of t and t bar respectively arises from the invariance under these transformations, provided tzz bar is 0. So you can identify the currents associated to the symmetry transformation as the product of the gauge parameter and tzz. So this is just in order to get something that looks like a vector. It's not strictly necessary. It's just that Tong, whose lecture notes I've borrowed some of these calculations from, uses this notation. This is not a bad one.
I do want to pause for a second to just remark briefly on the word current, which physicists take as extremely natural, and for everyone else, it's just like, where does this come from? Well, there is a fundamental concept of a current, which might come from electromagnetism, which is definitely feeding into the idea here, but we don't need to go into that detail right now. Already the idea used to derive the notion of the stress energy tensor, that is to say, the variation of the infinitesimal variation of the action under an infinitesimal variation, the infinitesimal response of the action under an infinitesimal variation of the action defines the stress energy tensor when we restrict the class of variations. And here too, we're doing exactly the same thing.
Well, if for the benefit of the curious amongst our viewers, I'll just break my notes and show what the analogy is. So in electromagnetism, we have a Maxwell action coupled to some matter fields.
Yeah.
Right. And what do? I vary this action with respect to the gauge field.
That's right.
And by definition, let's say it's in D dimensions,
So we've
that
got a
defines
tiny tangent vector in the space of all gauge fields, and we move a small
exactly
amount.
the response is what I'm calling the current. And now, just for the benefit of the viewers, what this could look like in, say, QED, where you've coupled Dirac fermions
Right.
to the gauge field in 4 dimensions, is basically this kind of bilinear formed from the fermion fields.
Absolutely.
This is just an example of what the current could look like. See, the current is something that is typically built of matter fields just because you varied the gauge field in order to obtain it.
Right. And it'll always be a function of what point in the space of matter fields. that you
Exactly.
set. And in the
Yeah.
same way, you could symmetrically be varying the matter fields.
Yeah,
with a
and
similar construction.
absolutely. And so you see the analogy now is that I'm defining, you see, I defined the stress tensor from varying the metric. So in many ways, the stress tensor, so let me just expand that right here. So if I just took this expression and noted that in fact, this defines well, so you see, it actually defines what you mean by the stress tensor. So the stress tensor is to the metric what the current normally is to the connection, to the gauge field. Now, the only reason I'm calling these currents is that I'm using the generalized notion of the word, and I'm forming vectors by just multiplying by the gauge parameter,
Right.
or the transformation parameter, the
infinitesimal
conformal
change
transformation parameter.
to the holomorphic and anti-holomorphic coordinates.
So for now, the moral of the story is that holomorphy of T or anti-holomorphy of T bar are the other side of the Noether's theorem. So they're the conservation laws coming from invariance under holomorphic or anti-holomorphic coordinate transformations, right? And that's the classical part of the story. Now, to upgrade this to quantum theory, we need to go from Noether's theorem to the word identities.
Right.
So the word identities say that the divergence of the current, which was 0 in the classical theory, is also 0 in the quantum theory, except when the current sits right on top of another operator in a correlation function.
Right.
If it sits right on top of another operator, then the result of integrating that correlation function over space is the transformation that the current generates on that operator,
Right.
which is really neat. So if I wrote this without the integral, there would be a delta function on the right-hand side, right? There'd be a sum of delta functions, basically.
Yeah.
But it's basically, what it's telling us is that there's this information about contact between the divergence of the current and the operator of interest.
I mean, would you agree, Vasu, this is an expression of locality, essentially,
Yes.
in a really deeply fundamental way, which I don't think we'll be able to really touch on here, but maybe that's.
I mean, we won't even really get to touch on the derivation.
Exactly.
Of this,
but
but
maybe
let's
that's
take this to be definitional, for sure.
Yeah.
Just because the derivation that people like goes through the path integral, which in turn needs an action and a Lagrangian, which may not be available in a lot of our adventures.
Certainly in conformal field theory generis, one often has no action in sight. In fact, you can just work in the operator formalism and write down very fancy constructions and bootstrap very fancy constructions numerically without ever seeing an action in sight.
Yeah, and that's probably the way to go in general.
Yeah, in fact, seems much more powerful.
Yeah. So the next step is, okay, so let's just see where we're building up to. We're interested in meeting the integral formula, Cauchy's integral formula, which was a contour integral over something one-dimensional. So in order to meet that, let's just use Stokes' theorem to transform the integral over a two-dimensional region of the divergence of the current to just the circulation integral over the boundary of the current itself.
Mhm.
Again, exercise for the readers, work this out in complex coordinates. See why you'll get dz here and dz bar here.
Mhm.
And note that you just do the normal coordinate transformation, see how this one tensor transforms, and you get these two components.
Mhm.
And now you have the same expression as I wrote above. You have the word identity. Instead of having integrals over gamma, you have the integrals over
Boundary.
the contours that bound gamma. So we're making progress. Nothing has happened so far. I haven't specialized to any specific current. This is just complex coordinates plus Stokes
Universally
theorem.
true.
Exactly. Exactly. Now, what happens if the currents were purely holomorphic or purely
Mhm.
anti-holomorphic? Right? Well, what happens is that we're in business, because knowing that J is holomorphic means that the result of this integral is going to be given by minus the residue.
Right.
Why minus? Because I've put the I in the numerator here instead of the denominator, but it's just going to be proportional to the residue of the product of J and O.
Right. The current and the operator, which is sitting on top.
Exactly. And what does it mean to know the residue? Well, it means to know the coefficient of the simple pole.
Mhm.
So we have divined a term in the operator product expansion
Mhm.
of J and O. This is one of the best ways to meet the operator product expansion. So I'm not even going to go into detail about where it normally comes from
Mhm.
and what you should expect from it. So let's just say that we have this operator product here. We know that this has to be its residue. And so what does that mean? It just means it's the coefficient of the simple pole from everything we've discussed.
Right. Right. So I do want to pause here to say that generically for these conformal field theories, or their holomorphic or anti-holomorphic chiral halves, the operator product expansion, or at least the singular or non-regular parts, can in principle have arbitrary finite depth. And so it becomes an extremely interesting question when you consider the closure of all operators in your conformal field theory under the OPE. You can analyze the depth of the pole structure, and you can ask, what information about the theory is encoded in the higher order poles? And quite honestly, this is an active area of open research, is really understanding the semantics of these higher order poles. Already for conformal field theories with gauge symmetries, we find quadratic poles that you might not find in theories of, like, say, free bosons or chiral fermions, which I find deeply fascinating and find myself obsessing over almost every day.
Well, we'll find that Rice is probably going to be talking about, what he's probably talking about are what we would call descendants.
Yeah,
but
that's right.
Before we get to descendants, we need to know what the primaries are. And that's what we'll eventually get to. So far, we've already met one potential use of the integral formula. But let's go back to our stress tensor. Now let's give some meaning to some of the transformations that arbitrary epsilon of z, p of z generates.
Right.
So if epsilon of z was a constant,
Yeah.
then what is epsilon t generating? Well, just translations, right? So I just do a Taylor expansion around z goes to z plus epsilon, I get the derivative of O, right? Same thing with d bar, right? Or epsilon bar.
Get the d bar derivative of O.
What does that mean? That means that the residue is going to be d bar O. So we've picked out that term in the TO-OPE. Now let's go a little bit further. So rotations and rescalings correspond to these linear transformations. So z goes to z plus epsilon z, or z bar goes to z bar plus epsilon bar z bar. And the corresponding j's take this form, right? Just note that there's an extra z here. Now I need to know what the delta O means here, right? The delta O,
the derivative.
Exactly. So if I have an operator of weight delta bar, that means that under rotations and rescalings, it transforms in the following way. So its conformal weight, its weight under rescalings, is the sum of delta and delta bar.
Mhm.
Its spin is delta minus delta bar.
Mhm.
Exercise for you guys, figure out why these are the eigenvalues of rotations and dilatations,
Mhm.
right? So, and you have these additional derivative terms that come from expanding these in epsilon, just Taylor expansion. And then what we find is, sorry for the typo here, but I will make it all no.
Yeah.
Exactly. So you see, the OPE now has an extra second order pole.
Mhm.
Sorry, I skipped ahead a little bit. Why is there a second order pole, one may ask? The answer to that is that I have Z appearing in
Front of the derivative.
exactly in front of the derivative here,
Hmm.
which means that if I was to try and compensate for it, I would have to look at Z minus W squared, right?
Mhm.
So that the residue comes out the right way. This is nice, but we've only divined two of the singular pieces in the OPE between the stress tensor and some operators.
Mhm.
What we can do is specialize or focus our attention on operators for whom this is as singular as it gets.
Mhm.
Right? That at most with the stress tensor, you have a second order pole, right? And these are the operators we call primary.
Operators, right?
Exactly. So we could ask, well, what does that mean? Like, what does that mean aside from a statement about the singular behavior of their OPEs? So we'll work backwards. Delta O is the residue, right, of the transformation of the symmetry generating current multiplying the operator. And it only has these two singular terms. Right. So what does that mean? Well, that means that if I expanded Z in a Taylor series around W, or expanded epsilon as a function of Z.
Transformed Z, yeah.
Exactly. Then what I'll have, because of this,
operator,
exactly, that looks just like delta of epsilon prime W minus epsilon DO, right? And this is just an infinitesimal version of this very simple scaling rule, right? So primary operators are the ones that transform homogeneously under finite conformal transformations. Conformal transformations here, I mean holomorphic change of Z, anti-holomorphic change of W, of Z bar, sorry. So we've met one of the most
primal elements of a conformal filter,
exactly,
you'd say, is the spectrum of primary operators.
Yeah, we've sort of met the captains of this spectral ship.
Absolutely. I mean, in fact, for rational conformal field theories, which I won't define, let's say that they're some of the simplest conformal field theories in existence. And certainly for some others, like certain logarithmic conformal field theories, the whole conformal field theory, or at least when restricting to a particular chiral half, the whole conformal field theory can be understood in terms of the primary operators, which appear more or less like generating vectors in a certain representation of the underlying symmetry algebra.
That we would very much like to understand.
Yeah, we'll get there. I think we'll get there. If we keep going, we will get there.
Yeah. And so another thing that we'll see is what descendants are and how they scale. But before we get there, we should probably look at what the Virasoro algebra is.
Yeah, we should.
Of course, that's for next time. But you see, the derivation of the conformal Royd identities as statements of the singular part of the operator product expansion all descended from holomorphy and the use of Cauchy's integral formula.
Which at the end of the day, we claim is harmonicity in the appropriate coordinate system, which it's really remarkable that it seems all of physics can be reduced to this principle understood properly, that certain functions are determined by their boundary values.
Yeah. Yeah.
Initial conditions are everything in
Right.
physics.
Yeah. Well, this is one application. Another application of the integral formulae are in what are called dispersion relations that appear in various places. Where they came from was optics. The context in which I mostly think about them is in theory of scattering amplitudes.
Right. And we've got some material prepared there that
We
we
do have
might
some
do
material.
maybe even tomorrow, depending if we have time.
Yeah, we will definitely be back, people.
Yeah, we will be back, and we might analyze reggae theory from the point of view of some elementary holomorphic analysis.
Yes, that will be the goal. So we do have some time for Josh's questions as our one and only member of audience.
Our distinguished audience member.
Any questions, Josh? No pressure.
Yeah. No. Actually, I was wondering if you could talk a little bit more about the connection between this variation on the action of the metric and the stress energy tensor. Like you talked about that a little bit, and I lost the channel a bit. So
Sure.
what exactly is there? Because you made some analogy, and I think there was some equation or identity you used that said that the trace of the stress energy tensor in real coordinates is equal to the stress energy tensor in complex coordinates, and there's some relation that you had between the two. Could you explain that a little bit further?
Okay,
Yeah.
so there's
can I even give it before you respond, Pastor? Can I give an interpretation, which I was thinking we might need to discuss, is exactly how a physicist thinks about this response.
right.
Yeah.
Well, there's two separate things.
Yeah.
So first, what you're asking about the trace versus what happens in complex coordinates is basically the fact that when you transform from real to complex coordinates,
Right.
the trace of t is proportional to the off diagonal component tzz bar.
Okay.
So we're thinking of two nominally complex coordinates here. So we're thinking of a 2x2 matrix, both of whose coordinates are holomorphic. But of course, these are not really linearly independent in a strict sense, right?
Yeah.
So that's why it might seem a bit strange.
So basically, the statement here is that the trace vanishing is the same as this off diagonal component vanishing.
Yeah, in the ZZ bar coordinate system.
And furthermore, the statement of conservation of the stress tensor, right, when we write it out more carefully, is going to be something like statement. Yeah. So basically, the full statement in complex coordinates
is that the divergence of the stress energy tensor is given by the application of the del bar operator on.
Yeah, but usually what happens is that it's usually going to contain an additional piece. So but you see, if tz bar z is 0, then I don't have
0 is in the wrong place.
Oh, sorry about that.
It's okay. I can't type and talk at the same time either.
So you see, if tz bar z is 0, then you just have the statement that tzz is holomorphic.
Yeah.
So it's very important that this vanishes, that the trace of t vanishes to get to here.
Josh, it's nothing but the application of transformation from xy real space to zz bar space, and that zz bar space is not linearly independent. Like the crucial fact that you have to use, because z and z bar are complex conjugates.
Okay. All right, that makes more sense.
Adding them does something. Yeah.
Okay. All right.
So this is one part of the story. The other part of the story
is what I mentioned about this response thing.
Exactly. So
may not be obvious.
So basically, the action, right? It's so let's actually take a step back. Really, what are we interested in? We're interested in the generating function.
Yeah.
Right. So the generating function, I'll leave its arguments blank for now. It arises as a result of doing, say, a path integral over some fields of of the action with some fields and some sources.
Yes,
What does that mean? That means that Z is only a function of the sources.
that's right, because we've integrated over the remaining variables.
Exactly. Now, what we're interested in, so if we think of, okay, so let's take another step back. What we're trying to do here in calling this a partition function is think about a probability distribution for whom you have this sort of Boltzmann weight, right? So basically, this is like the Boltzmann weight for the probability distribution, who's normalized by Z, right? Something. Okay, I don't know how to LaTeX.
Live LaTeXing.
Live
skill we have
LaTeXing
not
is-
developed this far in life.
No, we haven't. But basically, this is what I mean, right? So you have some probability distribution for the field configuration phi given some sources J.
Right.
Right. So the point is that you have sources that are in some sense external.
Mhm.
Right.
Like
And
the
now-
theory is defined as a parameter, a function of the source.
Exactly. The
as a
theory is
parameter.
defined as a function of
We
these
really
sources.
have a family of theories.
So now, what we call currents are the response of the theory under varying a certain set of these sources.
Right.
Right. My notation is bizarre here because I've chosen JI. But let's say, look, you know that one of these sources is going to be the metric, right? So there's the metric, and then let's say there's a there's other stuff. When I vary with respect to the metric, then the response of Z is going to be given by the stress tensor expectation value. So this defines the expectation value of the stress tensor.
You can take this as a definition of the word response. in fact.
Exactly. So literally what I'm saying is that, you just functionally differentiate with respect to G, or basically look at look at what happens when you vary G a little bit.
Yeah, and then the partition function changes by some infinitesimal value for every infinitesimal variation of G. And we call this the response. And this is exactly the definition of a current, in fact.
Exactly, because you see that the current
And this
also,
it makes it clear that it's an infinitesimal quantity as well when we cast it this way.
right. So the expectation value of the current also comes from taking the derivative. Now, instead of having the source being the metric, you can have the gauge field, right?
Right.
So in some sense, when I write expressions like this, I'm thinking about this field theory sitting on a background of either some metric or on the background of some
Gauge field.
electric and magnetic fields, so some gauge field or whatever. So this is where the notion of these responses comes
Right.
from, basically.
And remember, the way we formulated this, whatever your theory is, it could have any number of sources. Maybe it's even an effective field theory and is a function of many sources. And that means those sources could be matter fields, they could be gauge fields, they could be metrics, stress energy tensors come out when we vary these metrics. And you can think of that as maybe a gauge field coupled to gravity, in which you have a metric as forming part of your background. And all of these admit this notion of variation and response. And mathematically, we're doing the same thing, but physically, we find that these variations all have wildly different semantics. And I find that rather beautiful too.
That's true. You have to be careful, right? Because strictly speaking, if you were doing QED, what does it mean to do that? I mean, what does it mean to look at Z of A, comma, whatever?
Right.
It means you have to do some sort of partial functional integration. You have to first integrate out the matter fields and then
Right.
the effective action. So yeah, I don't know if that helps, Josh, at all. But.
I think it did. I think you actually went a little bit further than what I asked,
Than what
but
you were
I'm glad.
asking.
Yeah, a little bit further. But I mean, I've come to expect that at this point. This is not a surprise.
Yeah, well, that's a
No,
logic.
no, no. That makes sense. I guess like the one other small question that I would have, if that's if you guys have time for it, is
I do
so,
need to
so
go
your end.
soon, but go for it.
It's just I guess would be what you're building up to, right? So you've obviously stopped here, basically saying that okay, so we have kind of like the primary spectra of real numbers for our operator product expansion, which kind of gets us to this initial model of a 2D conformal field theory. What are you building towards? I'm guessing like, is it a deeper understanding of 2D conformal field theory? Are you
Great
eventually
question,
building up to
Dustin.
like
What are we building?
like is it are you doing like the vertex product operator, which gets you like a non-perturbative understanding of of this
These
or
LPs?
what?
Yeah, so really where this series of questions came from, Josh, was I've been studying some very particular vertex operators, which just happen to be more or less universal for all vertex operator constructions. These lattice vertex operators, which also spookily, mysteriously, happen to be the very first vertex operators anybody ever defined in the dual resonance models. And it turns out every vertex operator anyone can ever define can be specialized from these particular vertex operators. So what we're really trying to build up to an understanding of those vertex operators and their OPE.
Well, it's a good question, because the thing is that we're trying to build up some understanding of what the dual resonance models are, right, and then what they became, right? So what they were, they started as an effort to explain certain phenomena people noticed
in hadronic physics.
Exactly, in hadronic physics. So you have some statement about some scattering amplitudes that you're trying to explain. And this was at a time where people thought about scattering amplitudes from a very bootstrappy perspective. So it was all
it was specifically for the strong interaction, wasn't it? Like it was specifically the S matrix for the strong interaction.
Yeah, that's what we mean by hadrons, basically.
I mean, so, but at the time, the idea was that you just need to look at various interesting constraints on the scattering amplitudes, and you constrain your way to the answer. There was a philosophy there.
Yeah.
It didn't work. Field theory worked, like quantum field theory and standard model worked. It's not dead. But what we want to do is sort of like give a bit of that flavor.
Yeah.
So we want to sort of like show how extending scattering amplitudes into the domain of complex momentum gives you some interesting constraints on what the amplitude can be, how crossing symmetry manifests, and all sorts of other weird things. For instance, the whole notion of Regge poles comes from complexifying angular momentum. And why would you do that, right? Also, once you do that, why do you have any guarantees that your function that you started with
physical in any sense?
First of all, why is it physical? Second, why is it going to be well behaved?
Right.
Like, why aren't there just dragons in the complex plane? Right. And it turns out that it's very important that there aren't. It turns out that for everything of physical interest, these functions, these scattering amplitudes, have to be pristine analytic functions that you can analytically continue. And as I was discussing with Raiz, there was no need. I mean, you had no guarantee for that.
Like, why should that be true? I mean, we don't have a physical derivation for why analyticity should hold, which is one of the mysteries of this theory. And nevertheless, it leads to this remarkably beautiful theory that is entirely self-consistent. And underneath all of that is the theory of vertex operator algebras, which happens to govern the entirety of analytic geometry in complex dimension one, and of course, the physicists had no idea at the time that they were stroking the belly of this beast.
Right. but you see, there's a second aspect to all of this, which is that the answer to which physical system manifested the kinds of behaviors that people were noticing for the hadrons were relativistic strings. And in order to understand the scattering amplitudes that people guessed for these objects, you need to actually sit on their world sheet. so sit on the surface that they traverse through their propagation in space-time. And that's where the 2D CFT methods become very important.
Right.
So we're trying to build up both of these sets of tools, and they crucially involve very basic
complex analysis over and over again, which is what we're finding. And it's no surprise because, you know, if you really want to make any calculation on the world sheet of that relativistic string, you need these lattice vertex operators, and they are fundamentally building blocks of complex analysis in the modern point of view. So turned on its head or going backwards, it's entirely natural, but we're trying to do it in the historical order. We're trying to.
We're sort of trying to get there.
Yeah.
So, you know, just think about why you would send the center of mass energy to some complex value.
Yeah.
What would possess you to do that? And why would you expect that things would be fine when you did that?
What hysteria is this? What?
So, yeah.
You try to do that in any modern physics and people will label you as a string theorist as insane.
Yeah, I mean, that does make more sense. I mean, this is reminiscent to a conversation I had with Atenisov, where I asked him, hey, you know, if you're going to do 2D conformal field theory, what math comes up a lot? What do I need to know? And he said, it's really just complex analysis. Like it just keeps showing up over and over again.
Yeah, now we understand. In fact, I was telling Vasu why that's true earlier, and the goal is to do a session on that eventually. Yeah. We're not ready for it yet, but there is
gonna get there.
There is an extremely beautiful answer that I think is almost like the pinnacle of modern geometry. Yeah.
Okay.
Yeah.
Cool. So, I will be doing all the exercises you've left for your readers at this point. I think they'll be compiled into a text.
We feel motivated that we have an audience of one, but that's how it starts.
That is how it starts.
You have a relatively consistent audience of one who will attempt most of the problems you will leave to him. Yes.
No, that's better than 50 people that don't give a shit.
It's better than 50 Clubhouse people who are all like isomorphic to Sky Nelson.
We're streaming live.
Yeah.
I was going to say, Reyes or Vasu, when you said, obviously quantum field theory works or whatever, I'm like, I think a lot of people on Clubhouse would disagree.
Yeah.
Well, let's leave our discussion of them to Clubhouse.
Yeah. Leave that on Clubhouse.
Yeah. And for now, I think that we can wrap up our little session over here because
I think so too.
It's getting late.
And
thank you again.
Got a wife to go home.
I have a wife to go home too.
Really crushing it.
She will probably not be happy at the hour at which I return.
Playing with his mathematician friend on MIT's campus for no good reason at all.
Yeah, but I have that to look forward to. She's actually wonderful. I'm sure that she'll forgive me, but not tonight. So.
All right.
So,
well,